Today we will learn about calculation of leakage reactance of power transformer. So this is the origin of leakage reactance. See here a transformer cross section is given. Primary and secondary windings are shown here on different legs actually. So in power transformer to minimize the leakage reactance, we actually use shell type construction, and in that both primary and secondary can be on the same leg, of course, but leakage still will be there. Now here, so you can see this flux path. So this path is not through the core. So this is core, right? So this path is not through the core, and this path is also not through the core. So whatever flux flows through the core will also link the other winding. So linking the other winding is important. Or this is common flux or mutual flux. This is mutual flux, and this is a self flux or leakage flux, because it doesn't link the other winding, so it is self flux. So associated with both, either this flux also, mutual flux also, and then leakage flux also, there will be inductance in the circuit. So associated with this leakage flux is called leakage reactance, and it is series component in the equivalent circuit, while that one associated with this mutual flux is the shunt component of the winding, transformer winding. So a current carrying conductor is always surrounded by magnetic field lines. So this is one fact. And as an analogy to the electrical circuit, the existence of magnetomotive force in the magnetic circuit, magnetomotive force is nothing but N into I. In a magnetic circuit leads to flow of magnetic flux, which is limited by the reluctance of the magnetic circuit. So this flow of magnetic flux is limited by the reluctance of the magnetic circuit. Here you can see the reluctance of this is core, and reluctance offered to the leakage flux is of that air. So with reference to a power transformer, the magnetic flux produced by the winding current has two components. One is the mutual flux or main or working flux, and the other is leakage flux. Main flux has a role, actually it participates in the transformation of the voltages and currents, but leakage flux is actually unnecessary. So let us see. So the origin of leakage reactance. Here shell type construction is given to you, and you can see the main flux lines, and then here two windings cross sections are given here. This is winding 1, this is winding 2, and separated by a gap. So you see actually, so this part is core, you can take it as, and this part is you can take it as the again transformer body. So again core only you can say take. So here this is winding 1, this cross section is shown here, and winding 2 here into this into symbol indicates the current going into the plane always, and dot symbol indicates the current coming out of the plane. So here in this cross sectional figure diagram, so the winding is simply shown as a rectangular block, but it consists of lot of conductors like this. In all of them the current will be going into means going into the plane, so towards downwards. So and in this also, so winding conductors you can imagine like this, and then current is coming out of the plane. So current direction is taken as reverse because of Lenz's law. Always it will happen like that. The flux produced by the primary will be cancelled out by the secondary. That's what will happen due to Lenz's law. Now here this entire winding is the thickness width of the winding is W1 you say, and this is W2 second winding, and then this WG we can represent it as air gap. This is the gap between the two windings. So actually this gap is for mechanical rigidity, it will be supported by spacers often made with paper or wood. So this is how the construction will be. Now the magnetic flux lines produced by a winding which either only partially link the other winding or do not link the other winding at all constitute the leakage flux. What is leakage flux? Leakage flux means the magnetic flux produced by one winding, say W1. So it either do not link the other way. For example, this line, this flux line is not linking the W2, and this flux line is also partially, it is going through half of the winding only, so not fully linking. So these flux lines, even all those indicated in blue color, they are linking partially only one of the windings only. So but this red one is linking both of them. So this is how this red one is mutual flux, and then these blue lines are self flux or leakage flux. The effect of leakage flux is represented by the leakage reactances in the equivalent circuit of the transformer, as we have already discussed about the equivalent circuit of the transformer. So the series reactance, that is whatever is indicated, is actually the leakage flux. Now due to leakage flux. Now since the reluctance of the core is negligible and compared to that of the air or non-magnetic medium, energy associated with establishment of the leakage flux is significantly higher. So energy associated with the establishment of the leakage flux is significantly higher compared to that in the that of the leakage flux. So then the total leakage reactance of the transformer may be approximately obtained by short circuit test. Okay, after making the transformer and then testing it, we can definitely have the value of practically measured value of leakage reactance. But for design purposes, you need to know in advance how to design, and then so therefore calculation assumes important. However, the configuration of the transformer windings has a significant effect on the leakage reactance, and thus a generalized method of calculation is preferred. Of course, you can always test in a laboratory, but you should also have a calculation procedure so that will help in design. Since the leakage reactance represents a major energy storage element in a power transformers, its accurate calculation is crucial to the overall design of a power transformer. That's what I have been telling you. Now next, leakage reactance calculation. Now a typical pattern of the leakage flux lines is shown in the figure. You can see here there are two coils here. This is primary coil of very slim primary coil. You can see this is how it is. So this is how the primary coil is there, and this is the secondary coil. Right. This is actual flux diagram of a transformer. So both are of course of same height it is taken, and one is having N1 turns, another is having N2 turns. So this is core, this side core, this is shell type construction, and this is ambient or next limb or tank, whatever it is. So the flux lines within the leakage, these are all leakage flux lines. See, they are coming from the core. Actually this is core, this side it is core, this side it is core, and this side also it is core. So they are leaking through the core and then coming like this. So these flux lines you can see, but one significant observation here is within the windings But for this region, if you neglect this region and this region, so rest of the region, the leakage flux lines are very straight. So in this middle portion, they are very straight lines and parallel actually. So as seen, the flux lines are predominantly axial along the height of the winding. However, towards the end of the winding means in this region as well as in this region, the flux lines tend to bend and the radial component becomes predominant. Radial component means now these are axial component, parallel lines. All these are axial components which are parallel to the axis of the windings. And since they are bending means there is additional effect, means parallel is disturbed by radial component. So radial component becomes predominant at the edges of the windings. Therefore, the length of flux lines which is to be used in calculations can't be simply assumed to be same as the winding height. It is not the same as the winding height. So some modification has to be done because the lines are not parallel there at the edges. So some modification to account for this has to be done. So as proposed by Dr. Rosi, the typical leakage flux lines having both axial and radial components may be replaced entirely by axial lines. See, both at the edges the radial component is there, that can be neglected, and then some appropriate height adjustment can be done. So instead of taking actual height of the transformer, you take a little bit different height. So empirically and then even theoretically some development has occurred here. So the equivalent height of these lines may be calculated by scaling the winding height by a factor known as Rosi factor. So the equivalent height of the flux lines is thus given by HR. So this is Rosi height, also it is called Rosi height. So actual height is HW, then it is divided by KR, that is Rosi factor. So we will get HR, that is the height that is to be used in the calculations. So now we can neglect the radial component at the edges, not actually at the edges, whatever radial component occurs, that can be neglected, and by taking the different height HR given by HW by KR, where HW is the winding height and KR is the Rosi factor, and KR is less than 1. So here again windings are given here. Now the winding height, actual height of the winding is this much only. Okay. So sorry, this much only. This is the actual height of the windings. Now what is done is, so this additional height is taken. So HR is the Rosi height, and now we assume that the flux lines are not bending anywhere, because this is for calculation and this approximation holds good based on Rogosi's observations. So now we are taking the flux lines to be axial only, straight line only, and then the height is different from actual winding height HW. So it is given by HW by KR, where KR is the Rosi factor. Now here again this is primary winding of W1 length width, and this is secondary winding of W2 width, and then this is air gap between them is also of WG width, W2, and then this is W1 you can take. So this is the cross-sectional view again. And then the Rosi factor KR approximately calculated by the following expression. This is what Dr. Rosi has found out. So here, this is the factor. Here all the details are given. HW is the actual height of the transformer winding, and W1, W2, W1 is primary winding, WG is air gap, W2 is secondary winding width, and everything, all other things are known here. So this can be approximately calculated using this expression. So that is the Rosi factor. And then leakage reactance calculation continued. As we know, the MMF produced by the load secondary current is exactly balanced by the MMF produced by an extra component of the primary current, so that the main or mutual flux remains constant irrespective of load. So actually in the transformer, the mutual flux remains always constant. So even under no load also, and even under loaded conditions also, what will happen actually, whatever MMF is produced by the load, immediately that is countered by the same amount of MMF in the primary side. So the current is in the ratio of the turns actually. So it gets adjusted to such a value that N1 I1 produced by primary and N2 I2 produced by the secondary are always equal and opposite. So neglecting the small magnitude of the steady state exciting current, which is even less than 5% of the rated current, the MMF produced by both the windings is equal and opposite. See, for our calculation of leakage reactance, actually there will be a little bit imbalance because of the no load MMF, but that can be neglected because under loaded conditions, whatever MMF is produced by the primary winding and the secondary winding are equal and opposite, and actually that is predominant, that is the more in magnitude compared to no load MMF. So for all calculation purposes, we can neglect the no load MMF. So and then do the calculations based on the load current considerations. That is, the exciting current can be neglected. We thus arrive at a typical MMF profile in the power transformer, which has trapezoidal shape as described in the ladder. So what will happen? So the MMF produced by primary winding is equal to the secondary winding, neglecting the excitation. Otherwise, next excitation will have a little bit of value 5% or something like that. So if we neglect that, the MMFs are equal and opposite, and then total MMF is 0. So therefore, MMF should increase and then decrease. So maybe in between it should actually stabilize for some region in the area. So that we will see soon how the MMF. The magnetic field intensity, which is expressed as the ratio of MMF and the mean magnetic path length Ni by R. So of the magnetic circuit, thus also has a trapezoidal shape. So let us see how it is. In this case, the mean magnetic path length traveled by the flux lines is the equivalent height HR. Okay. Yeah, let us go. Now we see this. We have N1 I1 equals to N1 I0 plus I1 dash. So, and N1 I1 dash is equal to N2 I2. Neglecting this N1 I0, we can say that N1 I1 is equal to N2 I2. Thus, N1 I1 is equal to N1 I0 plus N2 I2. Assuming I0 equals to approximately 0, mod of N1 I1 is equal to mod of N2 I2 approximately equals to Ni equals to peak of the magnetomotive force. Now here you see the cross-sectional view. This is winding 1 LV, low voltage winding, cross-sectional view. Actually it is cylindrical. It is on the transformer core. Core is this side. This is core, entire structure. This is core. And then on the core is also cylindrical, you can assume. And on this core, this first primary winding is there. This is also a hollow cylinder now, because the core part is not winding. So this is a hollow cylinder. And having certain width, the width is equal to primary winding width. Now then there is another winding. This is secondary winding, say Hvpe winding. This is again a winding of width W2. So width is given here. This is W2, this is W1, and in between there is a gap, which is air gap actually. Of course, spacers will be there, but that also can be considered as air gap only. This is WG, gap width. Now MMF, the flux lines are assumed to be from the top one to the bottom one, with Rosi height HR is used instead of actual height. Rosi height is used here. Okay. Now the total, inside the flux, inside the core, we neglect the drop in MMF because it is negligible reluctance, and here large drop we can assume, and we can, since we are neglecting the magnetic path, now entire this thing is MMF is dropping here from this point to this point. Now here what is happening here? So as the MMF, how to draw the MMF diagram. So here as we move here, this is x radial position, actually radial position. You might say this is x direction. So in this direction, if you move, what are all the ampere turns enclosed up to this point, up to, for example, x, up to x, what are all the ampere turns enclosed up to this point? So total ampere turns of the primary if is Ni, because N1 I1 is equal to N2 I2 equals to Ni. So Ni is same for both of the windings, because irrespective of LV and HV, the N1 I1 should be equal to N2 I2. Therefore, MMF of both of them should be equal and opposite, of course. So here you are increasing the MMF because it is the number of ampere turns, or the ampere turns enclosed up to this point is some fraction of N1 Ni. So that fraction depends on this width. So total Ni by W into X will be the whatever this is X, position is X. So it increases. This is a straight line, right? This is MMF. MMF equals to Ni by W into X. Some constant is equal into X. Y is equal to Mx, line actually. So this is how a straight line equally. It reaches the peak. Peak is equals to N into I. And then remains constant because here in the air gap there are no conductors. All are flux lines only. Therefore, no conductors are there. Therefore, no ampere turns are enclosed. Right? So it will continue like this, without any change. And then again, when secondary or high voltage winding comes into picture, then this MMF of this one is negative, because it will be equal and opposite direction, right? So again, Ni by W2, you have to think Ni by W2 into X, like that. So with some constant, it will be again a straight line which goes down like this and reaches 0, because we have assumed that excitation MMF is negligible. It reaches 0. Otherwise, there would have been a little bit different. But now it reaches 0. We can neglect that difference and all. So this is how MMF wave can be drawn for any winding construction. Now for this value of MMF, now magnetic field intensity is simply Ni by HR, MMF by HR. Why? We are neglecting the path inside the core. So therefore, this is Ni by HR. So this is what is this actually? Magnetic field intensity. Magnetic field intensity is simply Ni by HR. So this is how the MMF diagram can be drawn, profile can be drawn. But what about a radial direction? Do you have any ampere turns included in the radial direction? No, because see, along the height ampere turns are distributed equally, assuming both windings are equal. Of course, if it is not equal, we will see what happens later. So, in this direction, always the MMF, if you plot a MMF diagram in this direction, radial direction, always it is 0 only, no MMF, because whatever, for example, if you consider up to this height, whatever ampere turns are included, and whatever ampere turns are included in primary and secondary cancel out each other, and the net is 0 only. So, like this, in the radial direction, you will not have any MMF wave here, only axial direction you have this MMF wave. So, of course, we have assumed the approximation of Rosi that they are axial lines only, and with corrected height, we can calculate the leakage reactance. So, next, the MMF at any point is the number of ampere turns enclosed by flux contour at that point. It increases linearly from 0 at the inner diameter of the winding where no turns are enclosed, and up to its peak value Ni at the outer diameter. Full turns are enclosed. That's what we have seen just now. Beyond the outside diameter and in the air gap region, the MMF remains constant because there are no ampere turns. It remains constant at the peak value. Since the flux contour still encloses all the turns and there is no additional turns, so it remains so until the outer diameter of the other winding is reached. Now, beyond this point, the MMF decreases linearly when it touches the other winding or X value. Then from there, by virtue of Lenz's law, the MMF directions are opposite in both windings. So, and becomes 0 at the inner diameter of the outer winding. This leads to typical trapezoidal profile. So, the profile whatever is given here is of trapezoidal nature, right? So, that's what is mentioned here. And then a cross-sectional view of the windings are given here. Top view of the windings are given here, because now we have seen the only rectangular boxes, but that is when it is cut like this. So you can see the cross-sectional view like that. But top view, if you see, so here this is the diameter of the core. This is DG. This is the diameter of the core DG. D core you can say. D core. Now each winding, this is W1. This is W1 width, and this is W2 width. Okay. Now each winding you can assume a mean diameter. Middle point, somewhere in the middle point. This is a D1 you can say, and again the middle point from here to here you can say D2, and similarly DG. I have drawn radius only. Please extend that line to the other winding for D1, and this is for last winding D2. And then there is DG already indicated with blue line here, you can see. So this is air gap actually. In the middle portion of the air gap you can take, and then from this point to from bottom, this point, it is DG, diameter of the air gap, mean diameter of the air gap. Now actually the diameter of the core itself is so huge, you can assume D1 is approximately equals to D2, approximately equals to DG, equals to some diameter D. So this approximation can be done wherever required and whenever required, and for quick calculation also it is possible to approximate like this. Now, then leakage reactance calculation. Now, how to calculate the leakage reactance? There is, a relation actually between energy stored in an inductance. You might remember this is half Li square is the energy stored in an inductor. So, if we equate these two actual energy stored in the inductor, so then we can estimate L. So, there is based on the H, we do have the energy stored equation for energy stored in the inductance or air gap. So, here based on that we can estimate leakage reactance. So, the energy stored in the material of permeability mu in a magnetic field intensity H is given as E equals to half mu H square into total value if H is constant. But if H is not constant, you have to integrate that one over a value. H changes with this thing and then position or then half mu H square into dV integration over a volume V. So, total volume V. So, then if we obtain this and then after that equate that to half Li square, right. So, from this L can be obtained. So, logically what is expected is this I square should get cancelled because it should not depend on I square. It should depend on only geometry and then magnetic properties or then physical shape of the winding, etc. Other than that, it should not depend on I square. Therefore, ultimately I square should get cancelled. That is what is expected. Let us see how it will happen. Now, thus for a given material subjected to a known magnetic field intensity profile, the energy may be calculated from which leakage inductance can be determined. So, energy has to be calculated using half mu H square. Now, we know MMF, from that we know H value and we know the geometry of the transformer. Therefore, we can estimate energy and from that we can estimate leakage reactance. Let us see how it can be done. So, energy stored in the air gap. So, first we will calculate what is the energy stored in the air gap because simply here H is constant because H is equal to Ni by HR. Ni is the MMF divided by Rosi height HR if we do, we can obtain magnetic field intensity. H is MMF divided by Rosi height you are using HR. Actually, you have to use actual circuit length, magnetic circuit length. But here we are using this corrected height because of the neglecting the radial component of the flux lines. So, MMF by HR we are using. And then this in this region, in this air gap region WG, since the MMF is constant here, you can see it is trapezoidal and then here it is constant. So, calculation is very easy. Simply the energy stored is equal to the half mu naught H square into volume. Now, what is the volume of this air gap? So, volume of the air gap is given by this actually. Pi dg into Wg into height HR. Pi dg into Wg is approximately the surface area of this one, this cylinder. Okay, approximately. Of course, you can do accurately also, but this is approximately. Dg is the air gap diameter taken here, a middle point, and then pi dg is you will get pi dg means this length of the this circular path, and then this length of the circular path and multiplied by this thickness will give you the surface area like this, total surface area of the cylinder, that this surface area, because you are taking mean diameter and then multiplying with thickness, you will get the surface area. This surface area multiplied by height of the cylinder will give you volume. So, that is what is done here, this approximation. This is also approximate equation. You can do exact, you can find the exact volume of the cylinder, that is not an issue. But since dg is so huge, and Wg is so small, so you can make this approximation without loss of any accuracy, and for a quick calculation that will always help. So the value of H is given by this half mu naught into Ni by HR square. This is H actually, Ni by HR whole square. So the value of energy stored, not H, the energy stored in the magnetic field is given by half mu naught Ni by HR whole square. This is the energy stored in the primary, in the air gap winding, this is multiplied by the volume, then that will give you the energy stored in air gap. Okay, now once we obtain the energy stored in air gap, now we have to obtain the energy stored in the primary winding also and the secondary winding also. So how to obtain it? So little bit calculation has to be done here. Mathematical linear equation we have to use and then integrate that. Here there was no need of integration because simply energy is half mu naught H square, H is constant, and volume is approximated with taking the mean diameter of the air gap. So air gap energy is very easy to obtain. Then energy stored in the windings. So here H of x equation is given here, just now I told you. So H of x is equal to H peak, Ni by HR into 1 by W into x. So this total H peak has to be divided by the length of the width of the winding W1 say into x. So that's how it varies linearly. So this is y is equal to mx type of equation only. So this once H of x is obtained, now again you use mean diameter of the winding one, say D1. So and then you substitute in this equation half mu naught H of x in whole square into dV, which is once you know the mean diameter, pi dx into pi d1 into dx is the width of that strip in which you are calculating the volume. That is the, so this is the differential volume, and total this entire this thing is differential volume, small for a small length dx. Okay, the differential volume of the winding is given by this equation, and then half mu naught into H of x whole square. At position x we need that one. So Ni by HR 1 by W1 into x is the value of H of x at position x, and this is the total volume enclosed in differential length d of x. So now you have to integrate this and from 0 to W1, x is equal to 0 to x is equal to W1. If you integrate upon simplification, you will get very simple equation like this. Simple half mu naught n square I square by HR pi d1 into W1 by 3. So if you compare with the previous one, so here pi dg into Wg into HR. So this HR square will get cancelled and here only one HR will come. So similarly same here one HR is there already. So instead of Wg here W1 by 3, it becomes, the width becomes 1 by 3. That's what is the difference mainly. So similarly for W2 also we can do, the secondary winding also we can do. So it is simply half mu naught n square I square HR pi d2 into Wt by 3. So total energy is energy of primary winding, energy of secondary winding, energy of air gap. So total energy if you add, you can take out this term as common. Half mu naught n square I square by HR into pi can be taken common, and d1 into W1 by 3 plus d2 into W2 by 3 dg into Wg. So air gap, since it is constant, you are getting dg into Wg simply. But in the primary winding also, in the secondary winding also, since it is linearly reaching the 0 or reaching the peak, so you are getting 1 by 3 factor, d2 into w2 by 3, d1 into w1 by 3. So this is the effect of winding, winding. So whenever winding is there, then there it becomes one third of that one. So compared to roughly one third of, for the same width, it becomes one third. The energy becomes one third of the air gap. So that's what is to be remembered here. Now d1, this d1, d2, dg can be approximately taken as equal. Then if you take out the d as common, then wg plus w1 plus w2 by 3 can be obtained here. So if total leakage inductance of the transformer referred to either primary or secondary is represented by L and it carries a current I, the total energy is given by half Li square. Suppose you want to find out with reference to primary, then what you have to do is you have to take half L I1 square, primary current you have to take. So this L will be equivalent inductance referred to the primary you will get. So total leakage reactance you are trying to get here. So the total leakage inductance is thus obtained as, see here, please remember this total leakage reactance means primary plus secondary, both referred to the primary you are getting. So if you equate this half L I square to the whatever energy we obtained in the previous this thing, you will get the equation for leakage inductance as this: mu naught n square by pi by hr, and d1 into w1 by 3 plus d2 into w2 by 3 plus dg into wg. Very simple and nice expression here. So as you can see, there is no I term. It should not obviously depend on I term. Actually, entire this equation is except mu naught. Mu naught is magnetic property, and then n square also related to geometry factor only, but n square is number of turns you can say. So rest of the factor, this geometry factor, whatever is given here, is simply denoting the physical dimensions of windings, air gap, etc. So simply L depends on these factors mainly. Apart from number of turns, on these factors it will depend. So therefore, designing or minimizing L, you need to consider these factors only. That's what is the indicated message here. Now normally the dimensions are huge such that d1 is equal to d2 equal to dg equals to d approximately. So you can take out d also common. So when you take out d common, d into this becomes wg plus w1 plus w2 by 3, like this. You can replace this term, this entire term from this point to this point with this point, with this term. So this is how leakage reactance calculation can be done. Please remember this L is L of total total inductance. It's not of primary alone or secondary alone. L of total inductance referred to one of the windings. Which windings? If you use here instead of N, if you use N1, you will get total inductance referred to primary side. If you use N2, you will get total inductance referred to secondary side. So that is the one. L means L1 plus L2 dash in case of primary case, L1 equivalent say. So this what you will get if you use a N1 here, right? Similarly, if you use N2, it will be total inductance referred to the secondary.